let's go back to the exercise. Okay? So in the last week, not last week, on the Monday, actually we are a little bit confused. I make you actually confused about this question number 6, the heat balance. Okay? So when you have heat loss or heat gain from to the surrounding or from the surrounding, how we actually put this one together to calculate the heat balance calculation. Okay, that's what we want to do it again. So let's go back to the same question again, explain step by step more logically than the last class, and then try to actually solve this problem. Okay, so question number 6. This question is basically I have 2 moles of the aluminum solid and then 1 mole of Cr2O3 solid reacting together at the room temperature, and then because this actually make chemical reaction like this, so this will make Al2O3, 1 mole of the Al2O3 at solid state plus 1 mole of 2 moles of the chromium at solid state. This chemical reaction from this one to this one is very exothermic reaction. So exothermic reaction means I'm generating a lot of heat. Okay? So internally, if I want to keep the same amount of heat, then I have to consume this heat to increase the system temperature. Okay? So I have system and the surrounding. If I want to keep the same amount of heat inside of system, there's 2 ways. 1, no work and no change of the form. Just stay as it is. Then there's no heat change at all. Yeah? Heat content, there's no heat change inside of system. But if you start to have the chemical reaction inside of system, because the reactant and the product have the different enthalpy. Okay? So when you have chemical reaction, we're talking about chemical reaction is driven by the Gibbs energy. But however, during this chemical reaction, your enthalpy can become negative or your enthalpy can be positive, depending on the chemical reaction. Okay? But whatever is the sign, so when you have the chemical reaction, there's always change of the heat of your material. So from the system point of view, so let's assume I have, my system initially have this amount of heat, okay? And then by doing chemical reaction, my materials, the material inside the system have this amount of heat, and then because of the chemical reaction, I become more stable phase, okay, from the Gibbs energy point of view. And during that, if you actually reduce your heat, so the product, so reactant have the higher heat and product have the lower heat, then your system point of view, you feel like, okay, my heat was here and my heat become this one. Yeah? So your heat inside of system is lower than initial state. But however, I want to keep the same amount of heat. Okay? Then this amount of heat from reactant to the product will release out because of the heat difference. This heat have to be used again inside of system and then increase the product temperature. So the reaction is happening at the same temperature, but however heat is released, and then after that, if I want to maintain the same amount of heat level, then I have to use that amount of heat coming out from the chemical reaction, and I want to actually use that chemical reaction heat to increase the temperature of my product again. And then finally, even though your form of the material is changed, but your system heat is still same. Is it okay? That's actually the typically adiabatic reaction. Okay, there's no heat loss to the surrounding or heat gain from the surrounding. Okay, and during this one, you could have actually, in the most of the realistic cases, during this kind of process, you are always losing certain amount of heat to the surrounding, like a heat engine. You are losing the heat. Okay, then instead of going this one to the same level, you're going to stop somewhere in the middle. Okay, the temperature cannot go to the maximum temperature. Temperature will be set, the approach to the final or maximum temperature, but not really as high as the maximum temperature for the adiabatic reaction. Okay, so that's the actual question for number 6. And also now, the other case is, okay, let's assume I have this chemical reaction, so I have this amount of heat to increase temperature again. And then on top of that, if I have additional heat from the surrounding, then that additional heat will be difference between my initial to the final. So it's going up again, further. Okay, this could be possible too. Okay, depending on the question, whether you are adiabatic condition, heat loss, or heat gain, you can have completely different story. Okay, the concept is same. Okay, however, the way you actually can calculate, or you have to take into account one additional term basically in this kind of calculation. Okay, so we have this kind of chemical reaction, and this produced a lot of heat number 1, for example. And in this case, this should be the negative term, but however, let's assume this kind of heat is in or out during this chemical reaction. And this is 298 Kelvin, so 25 degrees Celsius at same temperature. As I mentioned, chemical reaction happen at same temperature. You cannot do the calculation of chemical reaction at the different temperature by one step. You have to do first isomer calculation, and then you have to increase the temperature. Or you have to increase temperature and then do the isomer calculation again. Either way, okay? So if you look at this one, 298, 298, okay? And then, because of this amount of heat, for example, is released, then I'm going to increase this one to the certain temperature, to the final state. And that final state, in this case, is given, which is say that the final temperature will be 1900 degrees Celsius, so 2173 Kelvin. And then in that final state, chromium solid become chromium liquid phase because the melting temperature of chromium is 2123 Kelvin. So at this temperature, chromium will be liquid state already. So there will be 2 moles of the chromium in the liquid state, and then there will be 1 mole of Al2O3 solid state. Okay? So this is delta H2. Okay? And then, I mean, during this process, you are losing certain amount of heat, yeah? So that's actually something we have to really take it into account. We have to be careful about the sign of this actually, the heat actually loss, okay? So, now if I actually just draw this one again as just the enthalpy point of view, as I mentioned the last time. So for example, this is the process, okay? And I have my initial state, basically this is initial. So this is my initial state. And this is my final state. Yeah. And from the enthalpy of the system point of view, and your initial heat and your final heat is different. So this difference is your heat loss. Yeah. So this will be delta H heat loss. Okay? And if you actually go into this 2-stage process, we are doing basically, we have intermediate stage. So this is intermediate stage or the middle stage, and then we go to this one. So this is delta H1, delta H2. Is it okay? So now if you actually just look at the heat point of view, let's think about this way. So if I add this delta H1, so going to the positive to the negative, so it's minus, yeah. And then this one, delta H2, is positive. And then if I add up this delta H3, the heat loss, then the initial heat and the final heat should be same. Sorry. Okay? Or the other way around. This heat, and so this 1, 2, 3, if I, so from this one, so let's assume, or I can say that this one, so this initial and final. So this plus this become 0. It makes sense? delta H1, delta H2, delta H3, assuming this is positive, then sum all these three together become 0. Is it okay? So going down, going up, and if you sum up all three, it becomes 0. Is it okay? So that's what we want to do. Okay? So delta H total delta H change of this reaction here become 0, and the total is this plus this plus this. Is it okay? So let's try to. So delta H assuming that we are assuming this is positive term. Okay? So I'm just considering this not system or surrounding point of view. Forget about that. We are just assuming that there's the heat loss and that's positive term. Then this sum of these three becomes 0 because we start from initial heat and going down, going up, and going up. So it becomes the total change from initial to the final state is 0. Is okay? Make sense? Make sense? Sujong, make sense? Good. If you don't say anything, I'm not sure whether you understand or not. Okay? So give me some actual indication whether you understand or I don't understand. Okay? Good. So delta H1, let's look at delta H1. Delta H1 is the chemical reaction at 25 degrees Celsius. Okay? So aluminum, so delta H1, 2 moles of aluminum solid plus Cl2O3 solid become Al2O3 this one is 298 Kelvin and all this one is also 298 Kelvin. Both of them is same temperature. Is it okay? So 298 Kelvin, 298 Kelvin become 298 Kelvin. Okay? If you look at the information here given in actually this the problem, so we don't have this kind of information directly, this chemical reaction information directly. But however, you have the two information, say delta H naught Al2O3 is minus 400 kilocalorie per mole of Al2O3, and delta H naught chromium oxide is minus 270 kilocalorie per mole chromium oxide. Okay, so this is standard enthalpy of formation. Okay, so delta H at that question, delta H not Al2O3 means, this means the enthalpy change of the standard chemical reaction. Yeah? So it's 2 moles of aluminum solid plus oxygen gas at 298 Kelvin. So this delta H of reaction at 298 Kelvin. This is what standard enthalpy of formation basically. Okay, you good? 298, 298, 298. And similarly, at 298 Kelvin, so I mean this should be 298 Kelvin. This means same thing, 2 moles of the chromium solid plus and this delta H of reaction. So I mean this is just the general reaction, but standard enthalpy formation means I'm starting from the elemental stable phase with another elemental stable phase become new solid phase at the room temperature. That's standard enthalpy formation. Okay, so if you look at these two together, I can actually generate this chemical reaction from these two equations here. Yeah, two reaction here. So if I make basically minus of this one, I can have this delta H1. Is it okay? So delta H1, what I want to calculate is delta H Kelvin minus delta H not at Cr2O3 at 298 Kelvin. Okay? So then this value is roughly, okay, so minus 400 kilocalorie and 270, so minus 130 kilocalorie per mole of this formula. Okay? So delta H1, we know the value now. Okay? So if this value is directly given, it's okay, but unfortunately it's not directly given, but from this two information we can generate this actually the chemical reaction, and then we can get actually the answer. So minus 130 kilojoules, so it means my initial state was here, my final state is this one at 298 Kelvin, not final, I mean my first intermediate stage like this. So it means I'm losing this amount of heat. So from, I mean, this amount of heat is decreasing, it means that heat should come out from the system. Yeah? So that heat is available now in the system. So it can, that heat can be consumed inside of the system, or that it can go outside of the system, depending on how you actually treat the heat now. Okay, so heat is available now. Okay, so delta H2, so we want to actually increase from 298 Kelvin to the 2173 Kelvin. And the form, I mean the Al2O3 become Al2O3, solid become solid. And chromium solid become chromium liquid. So there's the real, I mean phase transformation from the chromium point of view, but this is not really the chemical reaction like this one. Yeah. So we can actually do those calculations with a different temperature at one step. Okay, is it good? So second part. So delta H1, we know this value, minus 130 kilocalorie per mole. And delta H2, delta H2 is related to this one. Now the final product from the first step, Al2O3 solid at 298 Kelvin, because this is both sides is different temperature, plus 2 moles of chromium solid 298 Kelvin become solid at 21 Is it okay? So let's look at how can you calculate this one. So if you have this kind of chemical, or if you have this kind of the process, the heat change from here to here, heat change from here to here, summation of these two will be total delta H2, yeah? So delta H2 equal to, so difference of this to this one, heat change difference, delta H equal to integral of Cp dt from initial temperature to the final temperature. Yeah? And we have heat capacity for the Al2O3 given there. And the heat capacity from chromium, heat capacity for the chromium solid and liquid, and also we know what's the melting enthalpy of the chromium. We know everything, okay? So we can probably add those things. So first part, alumina, Al2O3, so Cp of Al2O3, it's 1 mole, so it's 1 mole, and dt from 298 Kelvin to the 2173 Kelvin, yep. That's alumina part. And then second part, chromium part. First of all, we have 2 moles of the chromium, so 2. And then chromium become solid to the liquid in the middle, in the middle of this process, yeah. So we have to heat up the chromium from 298 to the melting temperature, the chromium solid phase, and then we have to melt it, and then we have to increase temperature again for the chromium liquid phase from melting temperature to the final temperature. Okay? Because we have phase transformation. So this one, integral from 298 to the melting temperature, Tm, and that Tm is 2123, so this is 2123 Kelvin, and Cp of the chromium, in this case solid phase, solid state, and dt plus delta H of the melting, in this case per mole, and so it's, if you like, you can make a small HO melting or HO fusion, it's the same actual meaning, plus integral Cp of the chromium liquid state from Tm to the final temperature. Okay? So then we have alumina part, solid, and chromium from solid to the liquid state. That's delta H2. Okay? And then delta H3, that's what we want to calculate, how much heat loss we have, yeah? So, now if I know this one, if I enter this one, and I can get what this value, because this should be, according to this concept, this should be 0. Okay? And when you say, okay, what's the heat loss, what's the sign? Is it positive, is it negative? It's really depending on subjective. I mean, how you look at actually the value, yeah? The absolute value plus, is it heat loss or is it heat gain? That's important. So, depending on how you set up the equation, it could be minus value, it could be plus value. But the absolute value, and then you have to know the direction, whether it's going out, going in, at least. That's important. So this amount of heat loss, positive heat loss, okay, you have to say, okay, what's actually the direction? Is it going out, coming in? Okay? Sign is not very important. You have to know exactly what that actually mean, okay? That the value, what's that value really mean? Is it really going outside or is it coming from outside to the inside? From surrounding to the system. Is it okay? So this one, I mean, we say that, okay, we know the final temperature, so we want to actually know what's the heat loss here. But as I told you, I mean, I can make this way. Okay, I can give the heat loss to you. I can give this heat loss to you. Okay? And then I want to calculate what's the final temperature. This is actually more tricky. Final temperature. So if I give the heat loss, a lot of heat loss, okay, then the final temperature may not be, or maybe lower than Tm temperature of the chromium solid phase, okay? Or if the heat loss is very small, it can go above this temperature too, yeah? So depending on the case, you have to test two different conditions, okay? So you can the first one you can do it, okay, I know the heat loss, for example. I know this value, I know the heat loss. I have to calculate this delta H2. Delta H2 is given in this way, and this is assuming that my final temperature is higher than melting temperature of chromium. Okay? Once you do that, and once you do all the calculation, and you can find what's this final temperature here. So this will be unknown basically in that case. And then you do the calculation, and then you see that, okay, delta H2 cannot be that value. It's too big. Then you cannot actually make this one become 0 under that condition. Then you say, okay, at least temperature should be lower than melting temperature. Then you have to do it again. So forget about this one, only concentrate up to this one, assuming this is question. This is actually the unknown value. And then you do the calculation again, make sure actually this can come out correctly. Then if that is actually come out correctly, it means your final temperature is lower than chromium melting temperature. Okay? So when you have phase transition, and if you don't know whether this is above the phase transition temperature or below the phase transition temperature, unfortunately, you have to do the test for both sides. Okay? If one of them makes sense, you don't have to do the other test, really. But however, if you are not sure, then you have to test both of them. Okay? Good. I like this kind of question. It takes time in the beginning, but I mean, once you know the method, this is the most important step here. Once you set up schematically how does the heat actually coming in and out, then the rest of them is just mathematics. Okay? Okay, next question. It's become a little bit more confusing now. More component. Okay, this is the methane frame temperature. Okay, so the methane CH4 is burned with the stoichiometric quantity actually. It's QAN, there's one missing here. Quantity of air. Okay, so there's the methane. CH4 is burned with the stoichiometric quantity of the air, and air is 21% O2 and 79% of N2. And that means what's actually the meaning of this stoichiometric quantity. There's no air or no. After chemical reaction, it's actually that's wrong. There's no oxygen or CH4 left. Sorry. All the oxygen in the air is consumed to actually burn CH4. Okay? So you have CH4 reacting with oxygen, become H2O and the CO2 basically. That's what it means. Okay? So when the combustion is completed, the product is CO2 and H2O. This is more or less we have learned from the chemistry in the high school, yeah? So whenever you actually burn something, you are pure, it becomes H2O and CO2. That's what it means. Methane, CH4 become CH4 reacting with oxygen and it becomes CO2 and H2O. And the stoichiometric quantity of the air means if you have one mole of CH4 and you need a certain amount of oxygen to burn completely to the H2O and the CO2, that's actually the amount we are talking about. That's the stoichiometric quantity over the air. Okay? And if the methane and air is mixed at the 25 degrees Celsius and there's no heat loss during the burning process, so it means adiabatic condition. Okay? And calculate the maximum flame temperature. Okay? And then we have all those kinds of the numbers. So first part is, okay, we have chemical reaction for the 3 different type of chemical reaction. At 25 degrees, what is enthalpy of the chemical reaction? Okay? And then second part is the heat capacity of the different kinds of gas phases. Is it okay? So let's try to actually make this one, draw this one schematically, what we really want to calculate. Number 7. Okay, so let's assume in this way, simplest way. Let's start step by step, okay? So let's assume I have 1 mole of CH4 gas phase. And CH4 have to react with oxygen. It becomes Is it okay? So let's look at actually the multiplication factor for each actual reactant and the product. So I have 1 mole of CH4 and it should make H2O. So I have 4 moles of H. So this should be 2. Is it okay? And CH4, so I have 1 mole of C. So this should be 1. Am I right? So we just do the mass balance in the reactant and product. And then how many oxygen? We have 2 moles of mono-oxygen and then 2 moles of the mono-oxygen. It's 4. So this means this should be 2 moles of O2 gas. Okay? At least you have to know how to set up this one. It's not very difficult. Is that okay? So let's forget about air. So let's make a very simple case. So case number 1. Let's assume that there is only methane gas and oxygen gas. Pure O2 gas. Then we can just set up the chemical reaction in this way. And stoichiometric amount of the O2 gas. So it means if I have 1 mole of CH4, I need 2 moles of oxygen. Should react together. Is it okay? So basically, I have a reactor here. I have 1 mole of CH4 and then 2 moles of oxygen. I inject it at 298 Kelvin. I make chemical reaction, and then in the end, this will be H2O, and then 1 mole of CO2, and I don't know this final temperature. I assuming that delta H equal to 0 adiabatic condition. Initial final heat is same. So if you just look at the previous diagram, so this is H and this is process. My initial heat, initial state, and then my final state. The form of the material is different inside of the reactor, but however the heat, H point to be, it's the same heat. Okay, so delta H of this to this one become 0. Okay, good. Let's start from this one. And then we add up more and more actually, additional actually the complexity here. Okay, so if you just assume in this way, okay, so how can I actually then calculate final temperature, T? Okay, so you have the same problem. I have reactant product, different form. Reactant and product is different form, yeah? And then you have different temperature. So you cannot do this kind of thermodynamic calculation by one step. You have to break down into the 2 steps. So one isothermal condition and one increasing of the temperature. You always have to do in this way. So whenever you see reaction happen and temperature is changing simultaneously, you cannot solve this one by one shot. You have to do it step by step, 2 steps. Okay? So at 25 degrees Celsius, 298 Kelvin, all this one, and then this is all T final. Okay? So that's what we want to do. And assuming that delta H of this chemical reaction equal to 0. Okay. So let's break this one down in this way. So we have this one first, 2H2O liquid phase plus CO2 gas phase at 298 Kelvin first. So this is 298 Kelvin, 298 Kelvin, and then we are increasing temperature. And if this final temperature is high enough, this could be liquid or gas. We don't know, yeah? Yep. Yeah. Could be. But at 298 Kelvin, you don't know, yeah? Yeah. Yeah. Hmm? Yeah. Third row. Yeah, H2 gas. If I don't specify here, it looks like gas phase, yeah? I mean, we know those H2 liquid is very difficult to get it. Yeah. So carbon should be solid phase. 2H2, H2 is gas phase. I'm sorry, I have to specify more carefully. And CH4 should be gas phase. And carbon, oxygen should be gas phase. Carbon is solid, of course. CO2 is gas phase. And H2O gas, I mean, we specified, I mean, this is H2O gas phase, yeah? It's not liquid phase. Okay, that's actually that value. And then the rest of the thing here, I mean, all of this is gas phase except for the H2O. It could be liquid or gas phase, and in this case, it's gas phase property. You okay? So, how can you do? How can you do? Very good question. So we need basically this one, delta H1, delta H2, yeah? And sum of total here, it means delta H1 plus delta H2 should be 0. This is total basically, yeah? Can you do it? I think this is only information. Do we have additional information? We don't have it yet. This is only information. How can I do? I'm even actually confusing. How can you do it? How can you do it? Can you do it? What do you think? Can you do it? Or you cannot do it? So let me ask you in this way. Assuming that this temperature is way above 100 degrees Celsius, 373 Kelvin. Combustion, yeah? I mean, this go to the above 3000 Kelvin actually. Okay. Assuming that, okay, this intermediate stage, do we have to really assume there's H2O liquid phase? I mean, this is chemical reaction. I am setting up whatever chemical reaction I can set up, yeah? This is imaginary step, yeah? Based on the available information. You can make any kind of Hess's law, yeah? So it could go liquid this one, or H2O gas plus CO2 gas become H2O gas phase. That's also possible, yeah? You don't have to really stick this is liquid at 298 Kelvin. Of course, H2O is stable as a liquid phase at 298 Kelvin, but in terms of thermodynamic calculation, I can even calculate the vapor pressure Gibbs energy or enthalpy at 298 Kelvin, yeah? H2O gas phase at 298 Kelvin, enthalpy. Yeah? I don't have to really stop what's the thermodynamically stable phase here for the thermodynamic calculation point of view. Okay? So, in this case, the first step, I assume this is gas phase, and then let's assume this is gas phase. And then if the final temperature is below 373 Kelvin, I have problem. But if it's above that, it should be definitely gas phase. Okay? So, we can get rid of that H2O liquid problem now. Okay? Just intermediate state, whatever you can set up. Okay, so now, if you look at this one, so delta H1, how can I calculate delta H1? So if you look at these three reactions, C plus 2H2O, CH4, and then if you combine them together, you can actually generate this one. So delta H1, I want to calculate, this is CH4, gas phase, plus O2, gas phase become 2 moles of H2O gas phase plus CO2 gas phase, and this should be 298 Kelvin, and this should be 298 Kelvin at same temperature. I'm going to calculate this delta H1. Okay? So if I combine the test 3 reaction, 1, 2, 3, C plus 2H, H2O, C plus O2, CO, and then H2, H2O. So if I combined reaction 1, minus 1, and then, so that chemical reaction, C plus 2H, and then C plus O2 equal to CO2, and then this one is H2, gas phase, yeah? So if I combine this one, so minus, plus, so I have 2 moles, I have 2 moles of H2O, yeah? 2 moles plus. Is it okay? Then carbon, and then 2H2 cancelled out. Yeah. And then O2 plus this one. So it's 1 mole and 0.5 moles. 1.5 moles of O2, which I need. No, am I right? No, that doesn't make sense. No, this is 1 mole and this is 1 mole, sorry. 2 moles of O2, yeah? That's what we need. And then we'll produce H2O and then CO2. 2 moles of H2O and 1 mole of CO2. Okay? So this is chemical reaction. I can combine together to make this one, yeah? In this way. So delta H1. So let's assume this is 1, 2, 3 reaction. Then delta H1. Sorry, it's not very good. So small 1, alphabetically 2. This one. Then this delta H1 equal to same as minus plus 2 mole. Is it okay? Can you get it? So we know the delta H1 now. Good? How about delta H2? Delta H2. H2 is simply heating up the temperature of the my product gas phase. Yeah? So delta H2 is related to the CH4, no, 2 moles of H2 gas, H2O gas, plus 1 mole of CO2 gas, become 2 moles of H2O gas, plus 1 mole of CO2 gas. And this one T final, and this one is T298 Kelvin. Yeah? So this means delta H2 is heat difference from 2 different temperature. So if you have heat capacity value, so you can just use heat capacity value for the integral. So Cp of H2O gas phase, from 298 to the T final dt plus integral Cp of CO2, and this is 2 moles plus Cp 298 to the T final CO2 dt. This is delta H2. Yeah. At the moment, let's just assume only there's CH4 and then reacting with only oxygen. There's no nitrogen gas at all. It's not exactly the same question. So let's start very simple case first. Because once you start to nitrogen here, it's more complex. So let's start the very simple actual case first, and then I'll add actual nitrogen after this one. So once you understand this one, adding nitrogen is very simple. So that's what I want to do. Is it okay? So, and then now, from general application, so now you have delta H total equal to delta H1, delta H2. Very good? So, we know the delta H1 value from the previous calculation. Delta H2 value have only one unknown. Yeah, I mean, it's not linear function, not the first order function, it's actually second order equation probably. So you cannot just do by your hand probably. You need probably reasonable calculator, or if you know the answer for the second order polynomial equation, I mean we know that, you can actually just use that formula and then get the answer. Is it okay? Good? Now let's really add nitrogen then. And let's make it also a little bit simplified this one. I mean, of course, air containing about 21% of O2, and 79% of the nitrogen. But let's make it simple. Oxygen is 20%, nitrogen is 80%. Okay? Is it okay? So, now case number 2. So, CH4 with air, and we are assuming air is 80% N2 plus 20% O2. Is it okay? Now, we have to actually change this one. So, for 20% of N2, I need 2 moles of oxygen. For 1 mole of CH4, I need 2 moles of oxygen to make this chemical reaction happening here, to completely burn the CH4. Okay? So, I need 2 moles of oxygen. Then how many moles of air I need? 10 mole? Am I right? Inside of 10 mole, 2 is O2. Is it okay? So it means I have additional 8 moles of nitrogen coming in the initial state. Am I right? So I have here at 298 Kelvin. So that's my input now. Is it okay? And then during the chemical reaction for this first step, what nitrogen is doing? Nitrogen, there's no chemical reaction. So nitrogen just hanging around without anything, okay? Just consuming the heat, basically, you know? So here I have at 298 Kelvin. And then, I mean, this nitrogen now, I have, so in this chemical reaction, it's okay. Okay, I have CH4O2 298 Kelvin, and this is also 298 Kelvin. Product, this, and this is 298 Kelvin. This one cancel out there. The same temperature, same material. It's canceling out. Yeah. However, when you now increase this product to this final temperature, now I have 8 moles of N2 gas phase from 298 Kelvin to the final temperature. This N2 consuming the energy now. Yeah? Is it okay? In this first calculation, so if you do this one, delta H1, CH4 gas, plus N2 gas phase. So let's just add here, N2 gas. It's consistent with everything else. I'm just adding this N2 gas here, 8 moles, yeah? And then here, I have also plus 8 moles of N2 gas phase at 298 Kelvin. This is same thing, same temperature, same material. There's no chemical reaction between this one to this one. So this can be just eliminated in this consideration. So delta H1 is same as the previous delta H1. Do you get it? No problem? Now, delta H2 actually have no difference. Delta H2 here, now I have plus 8 moles of N2 gas phase at 298 Kelvin. This will be plus 8 moles of N2 gas phase at T final. So, this calculation, now the temperature is different. So you have to add okay? That's difference. So basically, we're talking about here, I add 8 moles N2 gas phase. Okay? Yep. chemical reaction is only depending on the Gibbs energy, not heat capacity itself. Okay? And one of the assumptions here, we say that, so we say that, okay, when the combustion is complete, the product is CO2 and H2, and if methane in air is mixed at 25 degrees, no heat loss, and etc., and calculate the maximum frame temperature. I'm sorry. So theoretically, yes. What you say is yes. But in this case, we are assuming that there's no additional chemical reaction happening after you have CH4, H2 and the CO2. I don't get it. What do you mean? So do you mean this way? So do I have to this one at 298 Kelvin? No. Yeah. You could do that too. So this is one of the route. You can assume, yeah. So you can do it in this way. Okay. So I have this one, half of this one, half of this one reacting at 298 Kelvin, for example. And then the product will have this half of this one plus half of the initial material. And then assuming that at 100 Kelvin, that the remaining half of the CH4 and O2 is reacting at 100 degree Kelvin. And then you have now another product here. So you have to do, you can make another step, and then in the end this should be this one. Yeah? So you can go many steps. Or you can do, instead of 298 Kelvin, you can do this one to the 1000 Kelvin from the beginning. That's also possible. So I'm increasing this one to the 1000 degrees Celsius as it is. And then at 1000 degree, I make a chemical reaction. And then I heat it up further. That's also possible. Whatever you like. Yeah. Because of the Hess's law, yeah. Because enthalpy is state function. So you can generate whatever route you like. However, it's really depending on whether that is convenient for you or not, based on the available information. Okay? I mean, room temperature reaction looks very simple. That's why actually, and also most of the time, we have enthalpy of the reaction at room temperature very well known, very well given. That's why we are doing, typically at the room temperature, we change actually the form first, and then we increase temperature. But it doesn't have to be always like this. It's really depending on the available information. Is okay? That's your question? Any other question? Okay? I like this kind of question. So you have to know what I mean. I like this kind of question, yeah? But you already know this one. So if I actually make a question like this, I add a little bit more complexity. Can I finish first? Yeah. So what I want to actually add here is like this. Okay. So I have this become, okay, good. And how about this then? Okay. I have some heat loss during this this combustion. This is basically, combustion engine. CH4, methane gas with oxygen reaction. And you're making final product. And then during that, if I have heat loss, what would be my final temperature? That's one thing we can think about, yeah? The other thing I can think about is, okay, this reactor have certain material. So let's assume this reactor is the iron, Fe, or whatever, which can actually sustain the temperature. So, for example, Al2O3. And my Al2O3 is then, and then during the chemical reaction, if my reactor material, the reactor material is Al2O3, if that Al2O3 is increasing simultaneously to the final temperature, then you have to add on additional reactor material in the initial state, and then reactor material in the final state as well, yeah? And then with the heat loss. You get it? I can make any kind of additional complexity. I can add additional complexity here and then make it more complex and more complex very easily. Yeah, let's take a question first. Okay. Yeah. Yes, that's a good question. Typically, yes. Theoretically, if I want to give you exact information, I have to give whether this information 21 or 80%, 79, is it volume percent or mass percent? Yeah, but we know air quite reasonably well. So even I just give you in this way, you understand. But if you actually have this kind of problem in your midterm and the final exam, I'll specifically give you all the standard state, what's the state of material, what's actually the unit of the value more correctly. So don't worry about it. But if I don't give you, then typically in terms of the gas, typically in the available information in the literature, in the gas phase, they don't really say, okay, what's the mass of this fraction and this fraction. Typically it's volume percent. That's actually the usual assumption. So if you don't have any information, you can just assume that this is the volume percent. In terms of gas phase, in solid phase, now it's complex. Is it going to be more or mass? And that should be given correctly. Yep. Yeah, I'll give you the mass here. So I say, okay, 1 ton of reactor and reactor material is something. Well, I have to give you the mass here, of course. Otherwise, you cannot actually add, the equation here. Yeah, you have to know exact amount here. Any question? No. If I make it actually more complex for this kind of problem is, so in the first midterm, I'm giving a little bit hint, okay? Hint for the first midterm. In the first midterm, typically I'm giving you all this thermodynamic table for each question, okay? Probably in the final exam, I'll give you one huge table. You have to really go and then look at, okay, which information I have to take it out. That's a real, when you actually go to the the world, you have to do that. You have to know how to pick up the information first. That actually adds a lot of actual stress for you in the end. Any question? You good? Good. Okay, you'll do the very similar question for your homework too. Okay, let's look at the next one. So now let's look at the enthalpy change associated with freeze of the water at 273 Kelvin is minus 6 kilojoule per mole. Okay, so we have water, H2O, at 0 degrees Celsius, so 273 Kelvin, actually freezing enthalpy, so it means liquid becomes solid is that value, minus 6 kilojoule per mole over H2O. Okay, and the capacity of the water is 75.3 joule per mole Kelvin. It's constant. Okay. And then ice is also constant around this temperature, so that's 2 given. Calculate the enthalpy change when the water freezes at 263 Kelvin. So it's supercooling. Yeah. So water has to become solid phase, ice at 273 Kelvin typically, ideally, but as you know, most of the time we have undercooling. So, and if you know all this information, can you calculate what would be the real enthalpy when it freezing actually the water to the ice at about 10 degrees lower than the actual the enthalpy, actually the melting temperature or freezing temperature. Okay, this is actually very, very simple. Yeah? Because I know the answer. I mean, I can see it, and I can already see how to solve the problem, so it's a little bit easier for me, but for you, maybe a little bit confusing. So, H, enthalpy, and temperature. Okay, so let's assume I have solid, liquid water, so it's liquid water, and I have solid. And my usual actually phase transition temperature, 273 Kelvin. But now I'm freezing at this temperature, 263 Kelvin. My question is, what's this value? Yeah? And this value here is given. That's actually 37.6, no, 6.0. So this is delta H of melting, for example. Freezing is minus, so it's minus 6.0. Okay? And I want to calculate this delta H of melting at, so this is 273 Kelvin, 263 Kelvin. I want to calculate this value. And there's the information, additional information. Heat capacity here, the slope, this one is 75.3. So joule per mole Kelvin. And this slope here is 37.6. So if you look at this one, I mean, this is slope, yeah? So I mean, this is more steeper than this one. So with the decreasing, you will have smaller value than this one. Yeah? I mean, that's already we can see it from the graph. Okay. So can you really calculate this one? So basically, I want to calculate H of. So I want to calculate basically H2O liquid at 263 Kelvin become H2O solid at 263 Kelvin. This is what I want to calculate. Reactant product. Okay? And I want to use the Hess's law basically. So I want to increase this one, H2O, liquid state at 273 Kelvin. So I'm starting from here, going up here. So it's 1. So this is delta H1. And then I'm making the solidification of this one. So H2O solid at 273 Kelvin. So this is delta H2. And then I'm going up here. Solid 3, solid 263. That's this value, yeah? So this change is sum 1, 2, 3. Am I right? So this delta H of melting at 263 Kelvin. This is what you want to calculate. This is sum of this plus this plus this. Is it okay? Delta H1, liquid become liquid and just changing the temperature. So heat capacity here. From final temperature 273 and initial temperature 263. Okay? Delta H2, liquid become solid. So liquid have a higher enthalpy, solid have lower enthalpy. Yeah? Liquid have higher enthalpy, solid have lower enthalpy. So this to this one, so it's minus value of this one, yeah? plus delta H3 in the solid state from 273 okay? So most of the time, what we are doing is continuously just practicing Hess's law based on the available information. Is that okay? So next question. So we have enthalpy change at 298 Kelvin for 1 mole of hydrogenation for the combustion of the propane at the given below. Sorry. So C3H6 gas plus H2 is C3H8, and we have delta H of this chemical reaction. And then second one we have also this, and at 298 Kelvin. So it's a standard enthalpy, or the enthalpy of formation, enthalpy of reaction at 298 Kelvin. In addition, we know the enthalpy change of this one at 1 atm at this 298 Kelvin, like this. And calculate the heat relieved by the combustion of 1 mole of the propane at 298 Kelvin at 1 atm. So, propane. What's the molar formula? What's the chemical formula? So, the propane. Propane? C3H8? C3H8? Is it okay? That's propane? I don't know. So that's why I'm questioning. I have no idea. So let's assume C3H8 is the propane. Okay? You good? So C3H8 have to react with O2, and it should be CO2 and H2O liquid. So the second reaction. That's actually chemical reaction, yeah? And so during those kinds of the chemical reaction, propane at 298 K at 1 atm, how much heat can be released? How much heat can be released? I mean, there's no additional information we need here. So delta H2 is actually the value. So about 2,220 kilojoule of energy can be released. Is that okay? I mean combustion. So when you have the combustion of the any fuel, it becomes H2O and then CO2, yeah? I don't know why this question. Every year I always thinking, why there's this question. Next one, question number 3. So we have extraction of the zinc by the carboxylic reduction of zinc oxide and sinter at 1100 degrees Celsius, and can be represented in this way. So ZnO solid with carbon, and it becomes Zn gas phase and the CO gas phase. And calculate the heat of reaction at 1100 degrees Celsius based on all this information here, okay? So ZnO solid, carbon solid becomes ZnO gas phase and CO gas phase. Okay, I'm gonna calculate delta H of this chemical reaction. Okay, so ZnO solid phase. So first of all, I have to know what's the ZnO solid phase enthalpy. Enthalpy of ZnO solid phase at 1100 degrees Celsius, yeah? So reactant and product, enthalpy difference. So reactant, ZnO, enthalpy. So we have ZnO, H298. So H of ZnO at 1100 degrees Celsius, so 1373 Kelvin, is delta H of ZnO at 298 Kelvin plus integral Cp of ZnO from 298 Kelvin to the 1373 Kelvin. So all the information is given, yeah? So we can calculate what's the H of ZnO solid at 1373 Kelvin. Same thing, carbon. We have carbon enthalpy at 298 0 and then Cp. We can calculate that. And Zn gas phase. So Zn gas phase, you can calculate same way. But Zn gas phase, we have problem now because Zn gas phase I don't have H298. If I have H298 and CP, I can just do the one-step calculation. But I don't have it. So Zn gas phase enthalpy, in this case, should be calculated from Zn solid phase. So do you understand? I mean, we did all this one before. So when you have, so this is H. So I want to calculate this Zn gas phase, but I don't know this starting point at 298 Kelvin. Okay? And the one I know is this one, Zn solid phase. And then it melts, and then it vaporizes. So solid, liquid, gas phase. So I start from this one. I want to calculate this value here. I want to calculate this value. I know this value. Zn solid at 298 Kelvin. So I have heating up, adding up, heating up, adding up, heating up. Then all this difference, each of this one will be this value, this value, this value, this value, this value. So I know this final value. Okay? Because I know this starting value. It's 0. Zn solid at room temperature is 0. The standard state, it's material, reference material, yeah? So we have to do all those things, 3 steps, and then get the final Zn gas phase enthalpy at 1373 Kelvin. Is it okay? Good? And then CO gas phase. CO, it's simple because we have enthalpy H298 and the CP. So if you know the reactant product enthalpy, it's a subtraction of the product to the reactant. Then you get the final answer. Okay, next one. So calculate the standard Gibbs energy change of the following reaction. So far we have done enthalpy calculation, yeah? This is why we are spending a lot of time for the enthalpy. Enthalpy is very important value in the industry, actually, the process, okay? Heat is energy. Energy is money. That's why it's very important, okay? So now Gibbs energy. We have, okay, this, I want to calculate this kind of the chemical reaction Gibbs energy. CO plus O2 becomes CO2 at 1000 Kelvin. And we have 2 information is given for delta G of formation of CO equal to that value. Delta G of CO2 is that value. So that actually means delta G of CO, formation of CO, standard chemical reaction, standard formation Gibbs energy of CO gas. It means I have carbon solid plus half mole of the gas phase becomes CO phase, gas phase. That's what it means for that delta G. That stands for that chemical reaction. Okay? Gibbs energy for that chemical reaction. Is it okay? It's a standard enthalpy of formation. You saw that. It's the same thing. Standard Gibbs energy of formation of the certain material. It means it starts from elementally stable phase at room temperature and then become the final phase. Okay? That is already agreement. That's agreement between all the thermodynamic people. So you have to understand that's behind there. Okay? And same thing for the CO2. Delta G of G naught of formation. So carbon solid, 1 mole carbon solid plus 1 mole of oxygen gas becomes CO2 gas at room temperature. That's second one. So if you just combine them together, you can get those chemical reactions. Yeah? And delta G of reaction, same thing. I mean, we have HS, so it means when you have delta H of formation at 298, delta S of formation at 298, you can get the delta G of formation at 298. Delta G equal to delta H minus T delta S, and T is 298 Kelvin. You can just plug in the number and then you can get it. Okay? Simple, yeah? Heat is actually more confusing. But Gibbs energy, if I, instead of giving in this way, if I give the all the enthalpy 298, entropy 298 and heat capacity, you have the same kind of the complexity, but in this case it's much simpler. Okay, let's look at the last one. So, vaporization of Zn. So, Zn. So, boiling temperature of the zinc, I cannot pronounce it actually, Z very well. Zinc is the temperature, 1184 Kelvin, and we know the Truton's rule, yeah? So change of the entropy from liquid phase to the gas phase. That's about 90 joule per mole Kelvin. That's Truton's rule, yeah? And there was Richard's rule, Truton's rule. Richard's rule is solid become liquid, FCC, BCC become liquid phase. That enthalpy of melting, oh no, not enthalpy, let's say entropy of melting is about 9 joule per mole Kelvin. That's what is Richard's rule, and Truton's rule is change from liquid to the gas phase, entropy. Okay? So if you use that one, you can calculate delta S and delta H. I mean, delta S, we know, basically. That's Truton's rule. We know the melting temperature, vaporization temperature, and the S. So delta H equal to delta S over the T. No. Delta H equal to, no. Delta G should be 0 over the chemical reaction, liquid to the gas phase. Delta G equal to delta H minus T delta S. So we know the T, and then we know the S. So we can calculate H. H equal to T times T of vaporization times S of the vaporization. Okay? It's simple, yeah? Good. So we finished actually first part of our exercise. I will send you actually the information for your homework number 1. Okay? By email or by CTL message. Okay? You good? So part of them is from homework exercise. Part of them is your handout. So if you don't have a handout, please go to the website, CTL, and that's actually the handout is also uploaded inside of that actual website. Good. See you next week. Thank you.